Hello, Astronomy. Welcome to 13.4. Measuring the rotation of our galaxy reveals the presence of dark matter. Let's get to it. So we're learning about galaxies, specifically our galaxy, but much of the stuff we're learning can be projected onto other galaxies. So stars and gas all orbit the galactic center, and the orbital speed of stars and gas is fairly uniform throughout much of the galaxy. At first glance, that statement doesn't really seem to be like impressive at all. Like, I'm just kind of telling you, yeah, it goes around the center and it's pretty uniform. The speed's pretty uniform. You might be thinking, okay, that's fine. But the fact that it's uniform is actually really weird, because that shouldn't happen according to the rules that we know. According to like Kepler's planetary laws, right? The planets really far away move slower than the planets that are really close to the sun. So how come that doesn't apply to galaxies? How come the stars that are really far away don't move any slower than the ones that are really close? Generally speaking. So this statement already is strange if we stop and think about it. Since orbital speed does not decrease with increasing distance from galactic center, there must not be a single massive object holding other objects in orbit. Okay, so now we're explaining. I tell you the speed is uniform, and that's weird, because if there was a single massive object in the center that all the stars were orbiting around, it should act like our solar system. It does not act like our solar system, therefore we assume that there's not a gigantic center that everything's orbiting around. That's not to say that there's not a lot of mass in the center of the galaxy. There is. But our star is not orbiting specifically only that mass. Does that make sense? If you look on that bottom note, it says the mass of all of the objects in the galaxy keeps a star in its orbit. So the mass in the center of our galaxy does affect our star's orbit, but it is not the only thing that affects our star's orbit. Instead, the mass of all of the other stars in the galaxy also affect the orbit of our star. Okay? That's incredibly important. That's why it doesn't follow the rules that we think it should according to like our planetary rules. Because the orbit depends on both the mass down in the center and the mass everywhere else in the disk. Earth, for example, doesn't really care what Jupiter's doing. We just orbit around the sun, right? But a star definitely cares what all the other stars are doing, and it cares what the center of the galaxy is doing. So you can't compare them directly like that. Here's 3 examples of possible motions of the galaxy. And we're going to go through them, and then I'm going to show you which one is most probably true. We see on the left, it says the orbital speed of stars and gas around the galactic center is nearly uniform throughout most of our galaxy. That's what that first note said. We see these blue arrows are roughly all the same size. The stars in the smaller orbits gradually overtake those in the larger orbits. That makes sense. I mean, if every star is moving the same speed, and this track is much larger than this track, then this star is going to be done first, right? They're both going, I'm just going to make up a number, they're both going 10 miles an hour. This track is 100 miles and this track is 200 miles. Of course, the middle one is going to finish first, even if they're going the same speed. If our galaxy looked like a solid disk, like some people think, that means the orbital speed all the way out there would be a lot greater than the orbital speed down here. And you can see that in an example of a pencil. If this is like, let's say this, where my hand is right here, is the center of the galaxy, and let's say all the stars were on a solid thing. If you're rotating like this part of the pencil is moving a lot faster than this is, right? If I hit you with that, doesn't really hurt. If I hit you with that, you can actually feel it. This stuff is moving way faster. That is not the case with our galaxy, so we know that our galaxy is not a solid disk. And if our galaxy followed all the rules of our planets, that means that the planets down here would be moving much faster than the sun. The stars over here would be much. Oh my gosh, the stars closer to the center would be moving much faster than the stars far away, and that is not the case. So that leads us to believe that this is the way it works. The orbital speed of stars and gas is fairly uniform. That does not mean they're all exactly the same. There's a little bit of variation. We'll see that in a little bit. But it's roughly the same speed. That might be a question. I'm not going to go over it for the video. I guess we should. I've said it a couple times already, though, so I'm not sure if it's kind of beating a dead horse or whatever the saying is. Which would have a greater impact on changing the length of time it takes the sun to orbit the galactic center? Adding more stars to the galactic center, or adding more stars to the halo? The most important factor for how a star moves around the galaxy is how much mass is closer to the galactic center than the star. Notice it doesn't say the only factor, it says the most important factor, because remember the stars around it do matter, but the mass in the center does play the most important part. Right now, you're spinning on the Earth. The Earth is rotating around the sun, which means you're already going pretty fast. But the sun itself is going 790,000 kilometers per second around the galaxy, which means we are also doing that as well. So we're actually moving pretty dang fast. We just can't feel it because it's the normal for us. Don't worry about that. It just says that if the sun formed 4.57 billion years ago, then we've been around the galaxy 20 times. The sun's been around the galaxy 20 times. That's how big the galaxy is. From studies of the rotation curves of the galaxy, astronomers estimate that the total mass of the galaxy is about 10 to the 12th solar masses. So 10 times 10 times 10 times 10, 12 times essentially. It's not 120 times, it's not 12 times, it's not 10 times, it's 10 to the 12th solar masses, which is a lot of mass. Here we see a rotation curve of that mass, and what that means is the speed in which the stars orbit the center and the distance from how far they are at the center. Now, if they followed the rules that we think they should, the farther you go out from the galactic center, the lower the rotational speed is. But if you'll notice, the blue line is what it actually happens. Out there, it's actually higher, right? So there's something weird happening with the numbers here. The interesting thing about our galaxy is that we cannot see most of it, according to the math. Only about 10% of the mass is in the form of visible stars, gas, and dust. The remaining 90% is in some non-visible form called dark matter that extends beyond the edge of the galaxy that we would imagine when we say galaxy. Okay, so based off of all the math, we say there's 10 to the 12th solar masses in our galaxy. If we look at how many stars there are, just like taking a picture, there's not nearly enough stars for that to happen. If we look at this rotational curve, we don't have enough mass in our galaxy for this to even happen. So scientists then say, well, the math says we're missing 90% of the mass. It's probably out there, we just can't see it. The reason why we can't see it is because dark matter doesn't participate in electromagnetic radiation. Okay? That means that light doesn't interact with it. Not that it's black, light doesn't interact with it, which should barely make any sense. It means if you had a clump of it in front of you and you put a light on it, I don't actually know what would happen because it doesn't interact with that light. At least that's the idea of some of the dark matter. There's other explanations for dark matter, which we'll get to, I think, in the next slide. Here's what we think the galaxy might look like if we could see the dark matter. We got the visible part of the galaxy in the center, and then we got that gigantic halo of dark matter all around us. Stuff that we cannot see. And we think that that's the reason why all the stars behave like they do. Right? We said that it does matter what's in the center of the galaxy to depend on how the stars rotate. It depends on what the stars around are doing, but that's still not enough. We need to account for more effects, and the effects lead us to believe that there's some type of mass out there that we cannot identify. This is like cutting edge stuff still. So it's possible that even some of the stuff I'm saying right now is outdated. This book is, I want to say, 4 years old, and it's possible that in those 4 years we have learned stuff that some of this in like the next edition of this textbook might update. So how would the motion of the stars at the edge of our galaxy be different if there were no dark matter present? They'd be moving a lot slower. The fact that they're not moving a lot slower means that there's some type of mass out there keeping them going. That's why we think it's dark matter, stuff that we can't see. Now let's talk about the three, not the three, but three of the explanations for dark matter. We think it might be a combination of these three things: machos, WIMPs, and massive neutrinos. Machos are massive compact halo objects, which are dim star-sized objects. Imagine like brown dwarfs or white dwarfs who ran out of energy, that kind of thing. The stuff that's not really giving off light, but we can't really see it. Like if we could zoom up to it, we could, but we can't get that far, obviously, so we don't see that. So that's one explanation. Massive neutrinos is another explanation. And the massive neutrinos would be, remember when stars are formed, or stars explode, and they shoot off all the neutrinos, and they can pass through things, and there's so many of them, but we can't actually interact with them. We think that maybe there's just clouds of those neutrinos out there, and that's making a significant portion of the dark matter out there. We're not sure. There's some other fancier science reasons why we think it might be neutrinos, but that's just one of the explanations. And then this last possible explanation is a WIMP, or a weakly interactive massive particle. And these are the ones that would not interact with light at all. And these are the weird ones that I was trying to explain earlier. Scientists think that maybe if they could get a crystal to be super, super, super cold, almost absolute zero, and just watch it, eventually a WIMP might interact with it, and we can measure the interaction, even though we wouldn't be able to actually see what bumped into the crystal. But we haven't done that yet. So it's pretty interesting to think that the math says there should be this stuff out there, but we're not sure what it is. We can't actually find out of these three things what some of that stuff is. Although I would like to point out, we have found machos, but not nearly enough to account for all the missing mass in all of our equations. We have found machos, because those are just really dim stars or burnt out stars, like the white dwarfs that don't do anything anymore. We have detected those, just not nearly enough to make up for all of the matter that is missing from our equations. This is how we detected them. If they go in front of another star, they kind of magnify the brightness a bit. We can't see this weird object in front of it, but we can see the effects of it. So that leads us to believe that, okay, well, a brown dwarf is pretty dim, so maybe we just can't see that brown dwarf all the way out there. And it's just going in front of objects, and we can measure them that way. We can measure them that way. Remember, a brown dwarf never actually got to be a star. It's almost like a hot Jupiter. Like if a Jupiter got really hot and really big, but never became a star. That's what that might look like. So why are astronomers convinced that dark matter exists even though it hasn't been confirmed? I just got done explaining three of those things. One of them explains a little bit, but that means there's still like 80% of dark matter that's missing. Why do astronomers think that it's there? Why are they so convinced that it's there? Because as of right now, that's the best explanation as to why galaxies behave the way they do. We don't really have any other better explanations other than there's mass that we cannot interact with out there. That's a pretty crazy concept. I think we're used to science having most of the answers. Or if not having the answer, then knowing like, oh, we'll get there sooner or later. Or we have an explanation and it works like this. But like with this, this is still like new science. Right? Like this is still cutting edge, new stuff. One of you guys listening to this could find out what this stuff is in the future. That's how like new it is. And I think that's really cool. That's it for 13.5.